String instruments generate sound by vibration of strings. A string is displaced at some point along its length by being plucked, struck, or bowed, as in a violin. This generates stationary transverse waves on the string. A string fixed at both ends will normally produce a stationary wave in the simplest mode of vibration. This is called the fundamental mode. When plucked at other points along the string, other modes of vibrations are produced. Click on each overtone button. What do you observe about the pitch of the sound? Answer: the pitch of the sound rises as the overtone number increases. A musician will know that the rise between each overtone is 1 octave. Click Antinode. As the name implies, stationary waves are not progressive, so the positions of their peaks do not move. In the fundamental mode shown, the peak is always at the center of the string. The point A, where the amplitude of vibration of a particle is maximum, is called an antinode. Click Node. Since the string is fixed at both ends, the displacement at the ends is always zero. The point where the displacement of the particle is always zero is called a node. The screen shows a string vibrating in its fundamental mode. Drag the slider until the fundamental mode matches the proportion of the wavelength shown. How many wavelengths are equal to the length of the string? Answer: half of a wavelength. Derivation of the expression for the frequency of the fundamental mode. From the above animation, wavelength of the fundamental mode lambda 1 equals 2L. Hence, the fundamental frequency F0 equals V over lambda 1, which equals V over 2L, where V is the speed of the wave in the string. Click First Overtone. This is the first overtone or second harmonic. It can be formed by holding the string at the midpoint and plucking 1/4 from the end. How many antinodes and nodes are there in the first overtone or second harmonic? Answer: the first overtone has 2 antinodes and 3 nodes. Drag the slider until the first overtone matches the proportion of the wavelength shown. How many wavelengths are equal to the length of the string? Answer: 1 wavelength. If lambda 2 is the wavelength of the first overtone, the length of the string L equals lambda 2. Therefore, the frequency of the first overtone, F1, equals V over lambda 2, which equals V over L. What is the relationship between frequency of the first overtone to that of the fundamental mode? Answer: F1 equals 2 times F0, that is, the frequency of the first overtone is twice that of the fundamental mode. Click the second overtone. This is the second overtone or third harmonic. How many antinodes and nodes are there in the second overtone? Answer: the second overtone has 3 antinodes and 4 nodes. Drag the slider until the second overtone matches the proportion of the wavelength shown. How many wavelengths are equal to the length of the string? Answer: 1.5 wavelength. If lambda 3 is the wavelength of the second overtone, the length of the string L equals 3 over 2 lambda 3. Therefore, the frequency of the second overtone, F2, equals V over lambda 3, which equals 3V over 2L. What is the relationship between frequency of second overtone to that of the fundamental mode? Answer: F2 equals 3 times F0, that is, the frequency of the second overtone is thrice that of the fundamental mode. Select the appropriate values from the drop-down list for the fundamental mode, first and second overtone and click Check. Summary: the fundamental mode or the first harmonic has a frequency of F0 equals V over 2L. The first overtone or the second harmonic has a frequency of F1 equals V over L, which equals 2F0. The second overtone or the third harmonic has a frequency of F2 equals 3V over 2L, which equals 3F0. In general, the nth harmonic on a string fixed down at both ends is Fn equals n plus 1 times V over 2L, which equals n plus 1 times F0, where n equals 1, 2, 3, etc. These frequencies are called harmonics, and the series is called a harmonic series. The notes that can be emitted by a stretched string fixed at both ends are F0, 2F0, 3F0, 4F0, etc.